Very good. Well, thank you very much for the opportunity to contribute to this program for Venkat. What I'm going to do is not talk about my own work, but rather try to highlight for you some of Venkat's contributions, which have been in the area of applying AI methods to pharmaceutical engineering in general. And I'd like to point out, although Stratos already did a historical review, that Venkat actually did a postdoc at CMU that got him the initial flavor in AI. And then, of course, he went off to Columbia, where he began to accumulate some accomplishments. And one of the important ones was a conference that he organized in 1987, which had a few prominent people in it. George is just facing the other way, but I'm sure he's recognizable anyway. Also, Art Westerberg and a number of other people were at that meeting. And as you can tell, Venkat was just a charming youth at that time, barely out of the academic womb. But he made a very big impact through that conference. And as you can tell, his dean was really quite pleased at this activity. So it was a very auspicious beginning. But I'm sure the dean was probably a little disappointed because the next year Venkat came to Purdue. And as you'll see, Venkat has this habit of, leaving on a high note, which is not a bad thing to do. And I want to recount for you some of the accomplishments that he had at Purdue. I wanted to bring up this photo, which was taken at Purdue, which shows you the consequences of crossing the Hudson, going through Pennsylvania, crossing Ohio, and getting to Indiana. He aged prematurely in that process. But intellectually, he grew, so that was the positive part. Now, we already had a bit of a history, but I really wanted to give you the official history of his accomplishments at Purdue. In 2011, the school celebrated 100th year, and a couple of my colleagues, Phil Venkat and Nicholas Pepys, actually wrote a rather extensive history. And it is that history that is really the official history of Venkat's accomplishments. And I doubt very much where you can read all of that, but it basically points out, his academic background: University of Madras, physics at Vanderbilt, Cornell, PhD, assistant professor at Columbia, and then he came to Purdue, went through the ranks as associate professor, full professor, and then in February 2011 was appointed Riley professor. And as you notice, 2011 is when his tenure at Purdue ended. So it seems like he again chose a high note at which to depart. I'm interested to see what the next high note will be. But also in the official history, they listed some of the areas in which he worked and pointed out that he really was very effective in collaborating with colleagues across the campus. And indeed, in addition to collaborating research, he also was very effective in teaching. He received a number of teaching awards at Purdue, including being enrolled in the Teaching Academy, which is quite a distinguished step at Purdue. And again, if I go to the history, he contributed a very important course, Intelligent Systems and Process Engineering. And I don't know if you can read all of this, but this is my colleague Phil Venkat, who is a very truculent individual, and he pointed out that the course was taken by grad students, initially developed by Venkat in 1989, and then introduced artificial intelligence and application to process systems. He taught it this year, that year, following year, and then last taught it in spring 2010. And then Phil puts in the history. Unfortunately, the enrollments were low recently, that probably is an indicator of one or two things: Venkat's dwindling enthusiasm for AI, or the students' dwindling enthusiasm. I take it to be the fact that AI went through a trough, and it took it 10 years to come back again. Okay, so that's the the charitable interpretation of the history. Now, of course, he also did lots of things in research. In particular, we already pointed out 3 important areas that he was active in: fault diagnosis, safety, and product and materials design. And really what he did is to transition those areas of expertise and apply them to topics in pharmaceutical engineering. Major developments in the application of ontologies to organizing knowledge and models and decision processes for pharmaceutical product design and operation. Of course, also the detection and diagnosis of abnormal situations and process hazards. Now, I'm not really going to talk much about process hazards. Warren already did that, but I did want to tell you about the pharmaceutical area. And at the time, Purdue got involved with Rutgers in an NSF ERC that was focused on pharma. And so there was a pretty active team of researchers in mechanicals, chemical engineering, industrial pharmacy that, created a really nice environment for people, for Venkat to interact with, learn about pharmaceutical engineering, and apply it effectively. And as you can see, he's the center of attention here, clearly. Now, what are some of the things that he created? Well, one of the really early projects was really funded by the state of Indiana to a couple of $1 million, which was basically intended on trying to develop a decision support system for product formulation and product design. And Venkat very effectively collaborated with some industrial pharmacy colleagues who really lived in that environment and put together a very nicely structured system consisting of both structured and unstructured knowledge that one could apply to drive that process forward. And really one of the important ideas was the development of guidelines. Now, he kind of borrowed this from the AIChE documents that are issued, but I think the guidelines in this context was really making decisions, selection of processing routes, selection of excipients, and really taking into account the properties of the materials to actually decide the right decisions to make. Because this is really a product process design decision process. And this was really, I thought, a very innovative development published in 2006. I regret to say that the industry basically didn't pay attention, but to their own detriment. Now, he continued this line of research with recognizing that a very compact way of capturing knowledge was really through models, and that models needed to be organized. And so he built, with his students, Onto model, which was really a knowledge management framework for models. And I think this was really a very, again, early concept in how to structure. And what was interesting is he, very properly divided into the declarative knowledge, which describes the models, variables, parameters, assumption, but then also the procedural part was how you go about solving these kinds of models. And I think that was really very, really important in early development. Now, the ontology for models is really very classical. If you probably can't read the bottom line, but it has, all of the typical things about different types of equations and the assumptions in those equations and the parameters and so on. Very, very neat structure. Again, a little bit too early for its time, and this paper was published in 2010, but even that was too early. Now, I'm happy to say that in current research, we've actually adopted some of those ideas, and we have a group of people, including Dr. Casas here, who's really built a system called PharmaPy, which takes advantage of the object-oriented nature of Python to actually do something along these lines for the models associated with pharmaceutical processing, and also doing both the declarative part and the procedural part. So Venkat, really sowed the seed, but it only took us a dozen years to catch up. Now, the next big step was really the Purdue ontology for pharmaceutical engineering. And this was a system that had a number of components, but it had a rather unfortunate acronym called POPE. The reason it was unfortunate is because at the time, ontologies and meta-knowledge and what is knowledge and all of that was already rather mysterious to the community. So it was almost, philosophical, not really engineering. And then to have the temerity to call this thing Pope, essentially trying to declare this as a religious experience of some sort. And as you might imagine, both the industrial and the federal sponsors, they said, no, we have to have a separation of church and state. We just can't do this. However, the paper was published, so Pope was out there. But it was really a remarkable development because it really pulled together, in a very structured way, the information, the guideline ideas, and the mathematical knowledge into a very comprehensive system. And we really don't have the time to go through it, but I certainly invite you to take a look at the paper that was published in 2010, because I think it really lays out in a very systematic way all of the pieces of information that really go into developing a pharmaceutical product and process. And just by way of illustration, one of these components was really that of reaction prediction, predicting the degradants of a pharmaceutical product, because as you know, stability of the product and the generation of any kind of degradants that could be harmful to patients is really very important to product design. And so Venkat and his team basically put together an ontology system to address that. It drew on reaction databases in order to really populate and identify potential paths of various degradants. And implemented this within a protege, which was the vehicle of that time. So I think it was a very remarkable development, both this component and the fact that there was a vision to really integrate everything into a coherent system. Now, he also, of course, applied the expertise that he had developed with his students in abnormal events management. This is really a major area of research for Venkat since '87, and address the very classical problem of detect an abnormality, diagnose it, and then do something about it. Of course, we already mentioned the remarkable review papers that have stood the test of time over, well over a decade, 2 decades, in fact. What he and some of the students that work with him did then is to apply that specifically to pharma activities. And this is an example of a prototype system put together which really had multiple components. Of course, an ontology, you had to have that. I mean, how else could you, you couldn't just have a list. So we had an ontology of abnormal events. We had components that allowed us to analyze the data, so basically wavelets in order to denoise the data. Principal component analysis, Sal will applaud, to detect the event occurring. And then instances of a couple different diagnosis tools that would help do that. Now, the selection of the tools was really important in this context because these processes, particularly the one that they did an early application on, which was a continuous tabulating line, are really very fast processes. The dynamics is very quick, resonance times are quick. So if you're going to do diagnosis, you better be quick about it. And that drove the selection of the methodology. And they applied it to the classical, sort of icon of a problem, a roller compactor which takes material, pushes it through 2 rolls. The 2 rolls create a ribbon, and the simple control system is designed to control the roll gap by pushing more material through. So it's a very nice example that shows the illustration, illustrates the combination of control and an abnormal event. In this case, the abnormal events or all of a sudden material don't go through the rolls, right? They jam, or there's no feed. And this is a beautiful example, really very simple, but it illustrates that unless you capture that event, the control system will make it worse. Because if there is a plug in the nip region, the feed screw will just push more stuff in there until the system dies, okay? So this is really, I thought, a very nice application, and basically we're able to show that you can do the diagnosis in a matter of seconds, and you can intercept before the control system creates lots of problems. So, and that was, published, in a good 10 years ago. So if we kind of look at these examples, and these are just selected examples of Venkat's accomplishment, they really were groundbreaking. The ontology-based approach, it's taken the industry well over a decade to wake up to it. And there are now active consortia building ontologies for pharmaceutical engineering. There is a project that Lilly is involved with building ontologies. That's really, really exciting to see that happen. I think we don't quite or have reached the development of POPE, but I'm sure there will be a politically correct version of POPE that will arrive in due course. Also, of course, fault diagnosis is an area that's really gotten a lot of attention in pharma as well, and I think the version that we're now looking at is really condition-based monitoring, because we really want to look at both impact of control, impact of sensors, impact of equipment malfunctions, and that is captured within a framework of condition-based monitoring. So I think Venkat has really done a great job of pioneering these areas. Fortunately, he's not yet done. So I'm glad that we're celebrating 66, because that means he's got another 20 years to go, and by that time AI will go through the fourth wave, I'm sure. I did want to point out that among the active projects that Venkat was involved in, there's a collaboration with us at Purdue with a recently funded NSF program. We're really looking at the issue of distributed pharmaceutical manufacturing, and Venkat is contributing in the reaction path synthesis, so the prediction of reaction paths, as well as looking at the impact of disastrous events on the supply chain. How can we build a supply chain structure that will really be able to give us medicines in a reliable fashion? So I guess with that, I'd like to wish Venkat a happy 66th. And we certainly hope that you will continue to contribute to developments in pharmaceutical engineering, chemical engineering at large, and really, taking advantage of the third wave of AI. I think I'm counting it as a third wave, but I'm sure regardless of which wave it is, you'll have important insights to share with us. So, happy birthday.